Hello guys, how are you? I hope all is fine and welcome to the channel, which is notably Tech on Tube, and we are doing as usual, producing materials on basis of the concepts related to the aerodynamics aerospace. And with this topic, which is about the continuation from the last two videos, and it was about the lateral and directional stability. We have talked about the steady coordinated turn, and we have talked about the roll derivative, and now we're going to talk about the yawing moment, and which is obviously the directional stability in terms of directional stability, and the estimation of yawing moment coefficient, which is Cn of r. Yawing moment equation is in front of you, which is Cn is equal to Cnp Pb over Tv of t due to turn. Cnr Rb is 2Vt plus Cn beta into beta plus Cn alpha a lambda a into lambda a plus Cn lambda r into lambda r. Under the steady coordinated turn maneuver, and that is no side slip, p is equal to 0 and beta is equal to 0, it reduces to Cnr Rb over 2V of t plus Cn lambda a into lambda a plus Cn lambda r into lambda r. So this is how under the steady coordinated turn, obviously maneuver, we are dealing the steady coordinated terms, but obviously under the direction and lateral direction stability, and the no side slip, p is equal to 0, beta is equal to 0, it reduces to this one, because this one would be 0, this one would be 0, the remaining two terms would be this and also this one. And this equation indicates that rudder is held to counteract the moments due to the yaw damping, which is Cnr, okay, and the aileron yaw, which is Cn of lambda a. Okay, so I have actually explained as well what is yaw as well. Let me actually explain with the help of an example or figure. This is the aircraft wing, this is the tail in this upward direction, and these are the two tail as well, also with this wing, and also this is the whole fuselage as well. So the aircraft, when I'm going to actually talk in this direction, okay, with this axis, that would be roll. When I'm going to talk about in this, and I'm talking about in the direction anti-clockwise, clockwise, sorry, that would be yaw, and also with this axis, and you're going to turn it along this, which is in this direction, that would be pitch. So the yaw would be because of the aileron, okay, it is yaw is the directional moment. We just have to keep in mind, obviously it is in the vertical axis direction, so it is the directional moment, and we have to consider it as that Cn r Rb over 2V of t into Cn lambda a plus Cn lambda r into lambda r. This equation indicates that a rudder is held to counteract the moments due to yaw damping Cnr, okay, and the aileron yaw, which is Cn of lambda a, which this is Cn of lambda a. Okay, so if Cn lambda a is neglected, then obviously we have to consider that if Cn lambda a is neglected, if we consider it as 0, the remaining two, because of the aileron and because of the rudder, the yaw because of the aileron, okay, would be neglected, and we have just because of the rudder, it would be the yaw because of the rudder would be the dominating factor that will be counteract the moments, okay, because of the yaw damping Cnr and the aileron yaw Cn lambda a. So just solving it out, and r, and also proportionating r over lambda r into Cn lambda r by Cn r is 2Vt over b. Okay, generally Cn lambda r and Cn r are negative, that is negative. Okay, this one, thus one is expected to see one is expected to see r to be positive for a stable aircraft. Okay, one is expected to see R to be positive for a stable aircraft lambda R, also knowing the numerical values of Cn lambda R and lambda R into Vt, and B, the Dutch roll damping CNR can be estimated. Okay. So generally, C and lambda R into C and R are negative. One is expected to see R to be positive. This one for a stable aircraft. R by lambda R. Okay, this one. Okay, this one is a positive whole equation when the aircraft is stable. Also knowing the numerical values of C and lambda R. This one R, lambda R, Vt and B, the Dutch roll damping CNR can be estimated. That is the Dutch roll damping. Okay, so the Dutch roll damping CNR can be estimated. So we have to see that we have the Dutch roll as well, we have the yaw damper. This is the two combination. Okay, and Dutch roll is when out of phase. It is because of out of phase turn. We have to consider it, and yaw damp, obviously that will compensate that out of phase turn. We're going to use the yaw damper. So these are the two concepts. Because of the yaw, whenever there is a Dutch roll, there is a yaw damper. When there is a yaw moment, and also there's a yaw moment equation. There would be a yaw moment coefficient as well. That is also we're going to calculate with the help of an estimation. Okay, so the under the condition which is the steady coordinated turn. Okay, that needs to be considered, because obviously the turn is steady coordinated, but because of the out of phase turn, there will be a yaw created, and it has to be stabilized. The Dutch roll needs to be stabilized with the help of the yaw damper, and obviously it will help to create an coefficient, which is yaw coefficient. We have to estimate it. That is our purpose as an engineer, and I have actually explained you with the help of the figure as well, where how we're going to find a yaw, and how we're going to find a roll, how we're going to find a pitch. Okay, so these are the different types of actually scenarios that just pops up out of this moment equation, or from the yawing moment equation. So that needs to be dampened in as well. So this is obviously the position of the handling. There's starting from this, you need to go from this to this, this to this. They obviously the changing of the positioning of the handle, obviously that is of in the position of the pilot, and obviously the corresponding wing position will also be changed, and you need to have that into consideration as well, that the roll would be created. Whenever there is a roll, there is a right roll, there is a left roll. Okay, so because with the help of this wheel or handle, you can say that the pilot will going to roll, and there would be a when there is a roll, that would be because I have discussed earlier in the last video the roll derivative, and that is because of the lateral stability, and the roll derivative is the major part of the stability when we talk about the lateral and directional stability. And but because of the roll, there will be a yaw. Okay, and as I said, so yaw is because of the directional stability in the terms of vertical axis that I have shown in the figure as well. So it will be because of that one. So roll, which I have actually, we have calculated the coefficient as well. We have calculated the rolling moment equation as well from the last video, and because of the lateral stability, that is, or the stronger part of the stability. But because of that, we have the yawing moment coefficient as well. Because of the yawing moment equation, we create a yaw as well. That will be because of the yaw damper, and that is in the vertical direction, directional stability, that is weaker as compared to the roll stability or the lateral stability. So that this is how we're going to calculate. So flight test of estimate yawing moment. Okay, flight we need to actually test this equation. All the assumptions which are normally mostly are zero, beta is 0, r is 0, p is 0, okay, we have to consider that how we going to relate our assumptions to a flight test, and what are the possible steps that may come across, so that we can say that what are the assumptions that we took first initially were stand during the whole flight test, from starting from initially till the landing phase. Obviously the assumptions stand absolutely right, so that we can say our equation and also the flight test is absolutely okay according to the International Standard Atmosphere. So that is why we have to take it a test as well, just to say or just to check that what we have assumed is also being right according to the standards as well. So first of all, record the trade-off weight of the aircraft, take-off weight of the aircraft, and note down the velocity v, altitude h, rudder deflection lambda r, and roll angle phi during the steady coordinated turn maneuver. Okay, we have to consider with the help of the instruments we have discussed earlier. Now, given the value of c and lambda r, the other derivative c and r can be estimated with the help of the following expression. We have got this expression, we have actually derived it from our we have derived it from this from the Yawing moment equation as well. So this is the equation. Also plot the lambda r versus r, so slope will be negative. I have discussed earlier where since c and lambda r is negative, c and r would be negative, and the whole this form of the dividend and the divisor and the this whole actually quotient is also will be negative. So that is the point of whole discussion of estimating the yaw moment, just to calculate the weaker directional stability and of when the aircraft moves during flight. Okay, so in summary, because of last 3 lectures, what we have done, we have actually taken the experiments. We have actually from the last 3 videos were all about the experiments and testing, and from those videos we can summarize that lateral is roll, which is stronger, directional is yaw, which is weaker. Obviously that comes under the stability as well. Steady coordinated term, which was initially the starting point when you talk about in terms of lateral and directional stability, it comes about when we talk about the steady coordinated terms. We have obviously when there is a term there would be an angle, control angles for trim, okay, and derivatives for stability. We have to check the derivatives, the aerodynamic forces, the properties, and also the control angles. That may actually, that is the purpose of having that steady coordinated term, so that we can have the beta obviously is 0, theta is equal to 0, and phi is less than equal to 10 degree by assumption. So with the help of these control angles and with the help of the derivatives, we can assume that what if the steady coordinated turn is absolutely right, taking into consideration lateral and directional stability in terms of control angles for trim, not in terms of the yawing moment or the roll moment, but in terms of angles, control angles, and beta, alpha, theta, and we can assume that yes, the turn was steady, the turn was coordinated, and there was no slip. Obviously without any side slip, we have to take the lateral and the directional stability into consideration. This is obviously an assumption. This is all the estimations and approximation, just to see that what we can tabulate or record in terms of data is also being actually, you can say, is from one point to another is not falling behind, and we can say that at all the points during the flight, our assumptions are absolutely okay, and we can actually very sound, and it's the flight was very sound and according to the standard conditions. So that is the whole purpose, just to keep, and if there is any variations and if there are any deviations from our assumptions, we can obviously be there are the procedures to rectify, there are also procedures to counteract, even during the flight as well. There are numerous instruments and normally on the panel as well, which may help us to actually counteract and also neutralize, or you can say if there is any sort of the overestimation or even the underestimation, we can say that we have the equipments available so that the flight is absolutely okay, and say there is no such deviations from the standard conditions. So this is all about this electron stability, but obviously with the continuation of these concepts, we're going to calculate the coefficients as well. We have just calculated obviously we have calculated the moment coefficient, but with the help of this we're going to have some other test methods as well, just to have some more actually explanation of these coefficient, Yawing coefficient and roll coefficient, and also the side slip estimation. So we're going to have some couple of other videos as well that may help us to actually clarify our concepts about these coefficients as well. To hope to see you with this with the continuation of these concepts in a more explanatory form, and also in a more actually you can say practical approach, just to actually complete what we can actually get from all the concepts already been available in terms of stability or directional lateral stability whatsoever. So I'll end up the video. Hope to see you with in a short time with the interesting videos, obviously pertaining to the current concepts, and also to the current procedures of flight test and flight test methods. So hope to see you soon. Till then, take care and have a nice day.